Okay, good. So now we have the main concept. We want to draw from a complex distribution. And we have seen that if we are able to generate a Markov process such that the complex distribution is equal to the stationary distribution of the process, then it's very simple. We just run the process, simulate it, and then at some point when it has reached stationarity, we will obtain the draws we need. But of course, the key difficulty is to design this Markov process. And this is really what the Metropolis-Hastings algorithm is doing. So this takes the name of two researchers, and we will actually see examples of the two versions of the algorithm when I will deal with examples. So Metropolis was the one we introduced the concept, and Hastings generalized it. Okay, so let's look at the context first. So we want to draw from a complex distribution. What do we mean by complex? The target probability is defined as the ratio between Bj and capital B, and as we saw in the example, capital B in general cannot be calculated. Okay, so Bj is a quantity which is proportional to the probability. Capital B is the denominator to obtain the probability itself, and we assume that it cannot be calculated. And the objective of the algorithm is to simulate a random variable with probability mass function pi j. The main ingredients that we will use is a Markov chain that the user has to design in order to explore the state space. This Markov chain, this Markov process, has to be designed in such a way that we will explore the space in a rather efficient way. What does it mean, efficient? It means that it should not be too fast so that we would miss important points in the space. It should not be too slow either, because then it would take forever to reach important points. And this part of the algorithm is really the part that the user has to design based on the specific application. And I will give you examples about this when we will see the concrete examples. So for now, we assume that we have at our disposal a Markov process, which is characterized by the transition probability capital Q. And when I say Markov process, I assume all the assumptions that I mentioned before: homogeneity, aperiodicity, reducibility, and so on. Good. So this is the main ingredient, this Markov process, which is basically designed to explore the space. There is no assumption about the stationary distribution of this Markov process. Remember, our objective is to define a Markov process with a target stationary distribution. So what we will do is that we will build this Markov process based on the first one that we define. How? We will use the first one to generate a candidate. Okay, so suppose that we are now in state I of the process, and now I use my first process, the one that I designed to explore the space, to jump to another state, J, according to the transition probability capital Q. And now what I will do, I will decide if I keep this state or not. The next state of my new Markov process will be J, which is the proposed state by the first process, with some probability, and I will denote this probability alpha ij. So alpha ij is the probability to accept the candidate. And if the candidate is not accepted, I stay at I, which is the current state. And so this is with probability 1 minus alpha ij. Okay, so this is very simple. We design a first Markov process that is characterized by the transition matrix capital Q. We use it for simulation, and for each state, we decide if we keep the candidate or not based on a given probability alpha ij. Let's now calculate the transition probability of the new Markov process, the second one, and I will denote it by capital P. The probability to go from state I to state j in this new process is the combination of two things. It means that one, state j should be proposed by the first process, and this is true with probability qij, and it is accepted, which is true with probability alpha ij. So we have the probability to move from state I to state j when I and j are different. Now when I and j are the same, so what is the probability that the process stays at state I? Well, there are two reasons why we can stay at state I. The first reason is that the first process is proposing to stay at state I, and we accept it. So this is what is defined by this first term here. The second reason is that my first process suggests to go somewhere else, but this is rejected. And this is what the second term is saying. So for each of the other states, the state could be proposed with probability QIL and rejected with probability 1 minus alpha IL. So the transition probability of our new process is a combination of the transition probability of the first process and this acceptance probability that we have defined. Of course, this transition probability should verify the property that for each state I, the sum over j must sum up to 1. And if you do the derivation, you will realize that the value of alpha II must be equal to 1. So which makes sense, right? So it means that if the first process suggests me to stay there, well, I stay there anyway. And now we will use time reversibility. So remember, time reversibility links the transition probability with the stationary probability. So it says that pi times pij, so this is the forward part of the equation, is equal to pi j times pji, which is the backward part of the equation. And now we can replace pij by the formula that we have derived in the previous slide. Pij is equal to qij times alpha ij, and pji is equal to qji times alpha ji. And now we will derive the value of alpha from this equation. Actually, the value of alpha will depend on which one of the product between pi and q will be the largest. Okay, so if pi I times qij is the largest of the two, then the accept probability alpha ij will be equals to this ratio here, and alpha ji will be equal to 1. And you can verify if these values are used, the time reversibility equations are verified. And if pi I qij is less or equal than the other term, then we do exactly the opposite. Great, so now we have a value for alpha ij. Alpha ij again is the probability to accept a candidate. Well, we can calculate it. And how did we define it? By using the time reversibility equations. And now we have made the link between pi I and pi j, which are the target distributions that we want to simulate from, and the transition probability of the process that we have designed. The combination of the two give us the accept probability, alpha ij. So this can be defined as the minimum between this ratio and 1. And now comes the main property, the simplification. So if you remember, we have defined pi j as the ratio between a value, bj, and a denominator that I claimed that I was not able to calculate. But if you look at the equation for alpha, we need only the ratio of the pi's. And to obtain the ratio of the pi's, we don't need the capital B. It cancels out. So what we need to apply the algorithm is the ratio of the B. We don't need capital B. And this is really why these methods are extremely useful in the context that we have described. This denominator is not useful. The algorithm can be summarized as follows. You give me Q, and you design Q, which is the transition probability matrix of a Markov process that is designed to explore the space. And you also give me a target probability distribution based on numbers that are proportional to the probability. So I don't need to normalize them. Given these two elements, I define alpha, as we have seen, and then we create a Markov process that is characterized by capital P. So we generate a candidate from Q, and we decide, thanks to alpha, if we keep it or not. And this Markov process will have a stationary distribution, pi. This is exactly what we need. Therefore, when this Markov process has reached stationarity, it will give me the draws from the target distribution, as requested.